by the Chatelier principle. Alright, first of all, I want to do a simple demonstration on this. Alright, so now can you see my screen? Hello?
No.
Oh, you cannot? Oh, maybe I'm not sharing it yet. Let me see. Okay, let's share it now. Can you see that now? Can you see my screen now?
Yes.
Good. All right, you can see this. This is a balance, right? I just want to describe the scenario. This is like phenomenal. Now, if I want to, supposing I move this staple machine to this side, and this is not balanced again, what do you think I should do to balance it? Yes, I want response. You are watching me, so let's talk about that. I want to balance this back again. It was here. When I place it here, it was balanced. Alright? If I now move this pin to this side, it's no more balance. It's going to shift toward this side. What do I do?
You can move the left side closer.
Close. I can move this to this side. That will make it balance. Now, supposing this was the beginning again, it was balanced, and now decide to add one more weight to this side, and this side now becomes heavier and it's no more balanced. What do I do? Which side do I move the ruler to? Is it towards the one that has 2 or towards the one that has 1?
Shift the right to the left.
This is towards this side or towards this side? Towards the 2 or towards the 1?
2 to the 1.
Huh?
Move the 2 closer to the middle.
What do you mean by the middle?
2 to 1.
Is it towards 2 or towards 1?
Towards 1.
If I move towards 1,
2 towards 1.
If I move towards this side, it's go down more. I have to move towards this side so that I become balanced. Now the essence of this is to tell you that if a system is in equilibrium and something is added to the system which was not there at the beginning, the equilibrium will shift towards the side that is less disadvantaged. Now, this let me go back again. This is the middle of it. If I added one more weight to this place, this is my middle. Now, I want the equilibrium to shift towards this side, so that this side will now have a longer length. This is the shifting now. This side is now longer than this side. Normally, it's supposed to be the same length on both sides. When I get my equilibrium, this distance here should be the same. I'm looking at this length. From here to here, from here to here should be equal for me to get the balance. But if I now put more weight to this side, if this is more weight now, that means that this side needs to gain advantage. So this side needs to get more of that length. So what I'm trying to do is to shift the equilibrium towards this side that is having less advantage. Doesn't have any mass. This one has a mass, extra mass. This one doesn't have. So this side that doesn't have, I have to move my length to this side, because if you look at this length is longer here than this. So this side is gaining more ruler than this side. This side was disadvantaged because it has a lesser mass, compared to this side. So this side is considered to be the disadvantaged side. So I have to move my ruler towards that side so that the more ruler will be on this side. So this side has a smaller length of the ruler, while this has the longer side of the ruler. So this side was the disadvantage. My ruler will move towards that side. So that is what equilibrium is talking about. That in any system, if a system is disturbed, equilibrium will shift towards the side that is less disadvantaged. That is what Le Chatelier's principle is saying in essence. It says that let me go back to the PowerPoint first. This is a seesaw. So this guy has to be on the longer side for him to go down, to have the same length. So we're looking at this standard. We're not going to waste much time on that. We have a standard. Let's see for SC4. Let's see for regular class. Okay. So you look at this scenario. This is not in equilibrium. Why? Because this side is heavier than this. So you cannot say this in equilibrium. This is not in equilibrium. Alright? There are two types of equilibrium we want to talk about. Chemical equilibrium. We have reversible and you have the chemical. What do you understand by reversible reaction? I want response. When we discuss that a reaction is reversible, what does that mean?
It can go back and forth.
Very good. It can go back and forward. So the definition of that is a chemical reaction in which the products can react to form the reactants again. A chemical reaction in which the products can react to reform the products. So in other words, once you get your product, the product can also come together to form the reactant. It goes back and forward and backward. But in the chemical equilibrium, this is now the rate of the forward reaction equals the rate of the reverse reaction. And what is the rate? Rate is the amount of time spent to complete probably a journey or to complete a reaction. So let's say you want to go from your school, from your house to your school. You want to say, okay, what is the time? What time will it take me to go there? How many miles? Okay, maybe my house to the school is about 10 miles, and I spend 10 minutes to drive there or to walk there or to jog there. That means I have to divide the 10 miles by 10 minutes. That will give me the rate. The distance over time. That is your rate. So the rate, when the rate of forward reaction equals the rate of the reverse reaction, that means the time it takes for the forward reaction to be completed and the rate of the reverse reaction to also be completed. When they are equal, that's where we have chemical equilibrium. And this is an example. 2 molecules of mercury oxide, solid, in equilibrium with 2 moles of mercury liquid plus 1 mole of oxygen. Now this sign is what we use to indicate equilibrium. 2 arrows, one going forward, one backward. That means when this substance breaks down to form mercury and oxygen, this also combines again to form mercury oxide, and it goes on and on forever until when the equilibrium is disturbed. Alright? So this is Le Chatelier's principle. It says when a system at equilibrium is placed under stress, the stress is when you added a new substance, just like in the case of this diagram where I gave you. When you added a new pin, that is a stress. The system will undergo a change in such a way as to relieve that stress. So in other words, when I added the pin, the stapler pin to one side, the ruler has to move to the other side. Excuse me, to the other side, so that equilibrium can be maintained. So that stress is the extra pin I added to the left side or to the right side. and the relief is movement of that ruler to the one that has only one set of stapler pins. Alright, so let's look at the scenario now. Let's translate this. When you take away something away from a system at equilibrium, the system shifts in such a way as to replace what you have taken away. When you add something to a system at equilibrium, the system shifts in such a way as to use up what you have added. Equilibrium usually shifts toward the disadvantaged side. Let's go back to the class. Let's go back to the table. Now, this is in equilibrium. Let me add one more. You have to add one to this, so they'll be equal on both sides. I have to shift the equilibrium side. So this is my equilibrium. Le Chatelier's principle says that if the step is in equilibrium and a stress is added, what is a stress? A stress is in an extra load, excess load, or something you are going through. If I now add a stress can be in form of more weight to this side. Now when a stress is added, equilibrium shifts in such a way as to reduce the effect of the stress. So I'll move my equilibrium to this side. So equilibrium shift towards this side that is less, that has a lesser weight. That is what the Chatelier's principle is saying. Now when the equilibrium is balanced again, when I remove something, remove this, now this goes down because I'm taking away something. My equilibrium will shift towards this side again to balance the effect of removal. Alright? So, let's go back to class. It says that when you take away something from a system at equilibrium, the system shifts in such a way as to replace what you have taken away. When you add something to a system at equilibrium, the system shifts in such a way as to use up what you have added. So in other words, equilibrium usually shifts towards the disadvantaged side. Any question on that? On those two statements?
No.
Thank you for your response. Let's look at example 1. A closed container of ice and water at equilibrium. The temperature is raised in such a way like this. The temperature is raised. You have ice plus energy. The ice will turn to water, right? When you have ice block and you add some energy, energy is a form of heat. The temperature when the water is formed. And if this is in equilibrium, before we do that, you have ice plus energy. You have equilibrium. You have equilibrium with water. Now, the stress is the addition of energy. When energy goes up, what happens to the equilibrium? What happens to the equilibrium? Excuse me, sorry. Okay, let's go on. So what happened to the equilibrium? Because I'm adding energy to this side. Let me give you the clue. The equilibrium of the system shifts to what? To use up the energy. Where will your equilibrium shift to? Yes?
The right.
The right. You are absolutely correct. The right. Because remember I said when you add anything to this side, equilibrium shows towards the other side. Just like the ruler have to move to give more length to the other side. So that means this side was at disadvantage when you added energy. Supposing the energy was taken away, the equilibrium would have gone back to the left. Alright, that's example 1. Let's look at number 2. A closed container of N2O4 and NO2 at equilibrium. This is the equation. NO2 is added. That means the amount of NO2 goes up. Before then, the equilibrium was maintained. N2O4 plus energy to give you 2NO2. But you now added more NO2. The equilibrium of the system shifts to what side? To use up the added NO2.
To the left.
To the left. Thank you. Anybody with any problem with that? Everybody's good? Ariel? Andrian? John?
Yeah, I'm good.
Okay, everybody's good. All right. Right, example 3. A closed container of vapor and its a closed container of water and its vapor at equilibrium. Vapor is removed from the system. This is the equilibrium, water plus energy to give you vapor. You are now removing the vapor. When the vapor is formed, you remove it. Where will equilibrium shift to?
To the right.
To the right? You're right. That's correct. Because you are taking away this vapor, so that becomes a disadvantage side. Because for you to maintain the equilibrium, the vapor must be there. You must not remove the vapor for this equilibrium to be maintained. So in this case, because you are taking away the vapor, equilibrium have to shift to the right. Very good. Scenario 4. A closed container of N2O4 and NO2 at equilibrium. The pressure is increased. The pressure is increased. In a closed container, look at the question. In a closed container of N2O4 and NO2 at equilibrium, the pressure is increased. The equilibrium of the system shifts to the blank to lower the pressure because there are fewer moles of gas on that side of the equation. I've given you hints. So where will your equilibrium shift to?
Left.
Why?
Wait.
Because there are fewer moles.
Thank you. Because it has fewer moles. Look at this. This is 1 mole of N2O4. This is 2 moles. Remember, pressure is increased in a closed container. When the closed container is maintained, it means all these 2 gases are together in the same container. But because this one has 1 mole of N2O4 and 2 moles of NO2, equilibrium will shift toward the side that has a lower mole. Look at the hints here. It says to lower the pressure because there are fewer moles of gas on that side of the equation. This side has 1 mole. This side has 2 moles. So that means equilibrium shifts towards that side. Even though they are all the same container. And of course it's a closed container. So in this case, equilibrium will shift toward the side that has a lower mole. When you are considering gases this time around, both of them are gases. Alright? Good. Alright? Number 5. A closed container of N2O4 and NO2 at equilibrium. A catalyst is added. Equilibrium of the system shifts to where? A closed container and a catalyst is added. What happened? Yes, yes. We are almost to the end of the class.
Shift to the right.
Why?
Because the catalyst will increase the energy.
The catalyst has no effect. The catalyst speed up reaction of both forward and backward. Now, what you have to understand about a catalyst is a substance that changes the speed or changes the rate of reaction. The definition of it slows down the reaction or increase the reaction doesn't, to increase the speed of reaction is not only disproved, but it's not correct. A catalyst can affect both forward and backward reaction. It changes the rate of reaction. So in this case, because it's a closed container, because when this combine together to give the product, this also is now a reactant to give a product, which is the former reactant. So it goes forward and backward. In this case, a catalyst has no effects on the equilibrium shift. So take note of that. Anytime you have a catalyst, there is no effect on the equilibrium because it affects both sides as long as it's a closed container. Of course, if it's not a closed container, then it cannot reach equilibrium because it means it's only one-sided. It's going on one direction. Because as soon as this gas is produced, it's going off. It's going away. So it cannot maintain equilibrium in an open closed system. It has to be in the open system. It has to be a closed container before you can have equilibrium. In that case, equilibrium catalyst does not have any effect on the equilibrium because it can affect both sides equally. Both forward and backward reaction are affected at the same rate because the catalyst is inside the container. Alright, take note of that. Alright, let's look at a little bit of the temperature here before I give you the ticket at the door for the day. When the temperature is exothermic, for instance, -305, the heat is given out and the heat will be on the product side. When the temperature is endothermic, it's going to be a plus sign, +305. Just give you an example of the temperature. The heat is absorbed into the system. Hence, let me check hence your hence your heat will be on the reactant side. So that means when you are given the equation, if you have heat on the product side, the reaction is exothermic. There are two things to look for. Whether the heat is on the product side or you have a negative delta H. That will be exothermic. If the temperature is given as a positive value or the temperature is on the reactant side, then it is endothermic. Right? Any question so far before we call it day here? Any question?
No.
The temperature, the pressure, catalyst. Any other person? Any question?
Do we have more?
Yes, I'll give you a ticket at the door from here. It's just about 5 questions. Doesn't take time. There's no question. This will be your ticket at the door. Consider the equation above. N2O4 to give you 2NO2 and blah blah blah. What happens to the shift with the changes below? Increase that, increase that, increase that. Temperature is increased. NO2 or decrease. NO2 is decreased. So just answer those 5 questions and send it to me as soon as you're done. Any question?